Hi, this is Eric Sullivan with another ALP chemistry lesson on video. And this lesson is on thermochemistry, which is chapter 17 in the Wilbraham Pearson chemistry textbook. And this is a live recording, so you may hear me respond to questions from the class. And that's okay. If you're watching on a video, please bear with me. You may have some of the same questions as well. So let's get started in the lesson. So this lesson starts by talking about energy and the definition of what energy is. So energy is defined as the capacity to do work. And that could be any kind of work. In physics, they talk about work being the application of force through a distance. So that's one kind of work that would be energy. Other kinds of work could be electrical work, could be heat work. It can also be thought of as energy being the potential for causing changes. So when we think about work, we think about changes like moving something over a distance. We think about changing something's temperature. We think about lighting something up, so there would be a change going from dark to light. So for the purposes of chemistry, this second definition about energy being about causing changes is probably more useful, because in chemistry we're interested in changes from one substance to another, that kind of thing, and we want to look at the energy changes that go with that. Okay, so thermodynamics and thermochemistry is what this is all about. These are the technical names for this topic. So thermo being heat, and dynamics being change. So thermodynamics is really talking about heat changes, and thermo, again being heat, and chemistry is talking about heat and energy changes related to chemistry. And chemistry, again, chemical changes being about changing one substance to another. What we're really interested in is the study of heat and energy changes when a system changes or when a substance changes. So that's what this is about. So some things to know about energy before we get onto the details of this unit. One thing to know about energy is you can convert it from one form to another form. For example, we can convert sugar to the energy used to move muscles. And the energy used to move muscles can translate to motion of the body. So in that sense, we would be taking chemical energy and converting it to kinetic energy. You can also move energy from one place to another. So for example, the energy that is generated by the nuclear reactions taking place in the sun comes to Earth in the form of light, and then that energy can be used to grow plants and make food and do other things. We can take electrical energy and we can generate it at one place, send it through electrical wires, and have it do something useful at a different place. So you can move energy from one place to another. And the example that we have is, again, I mentioned that the sun generating light, which can be used to grow plants, and then the animals eat the plants, and so that goes from one place to another. Another simple example that the plants and the animals may get turned into food that we would get at the grocery store, and then as we eat it, it becomes us. So there's examples of energy moving from one place to another. There is a law, so again, this is a natural law, back at the start of the course. We talked about natural laws. Another natural law is the law of conservation of energy. And what this law is about, in any kind of process, like any kind of change, energy has to be conserved. And by that we mean that it can't just disappear, it can't appear from nowhere. You have to take energy from someplace and it has to go someplace. You can't just create it from nothing or destroy it so it disappears into nothing. In terms of units of energy, there are all kinds of different units used for energy, but the ones that we'll use in this course are the calorie and the joule. The joule being the metric unit for energy. So the calorie is defined as the energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And a calorie is equal to, hold on a moment, 1 calorie equals 4.184 joules. So if we want to convert between calories and joules, that's just a standard unit conversion. So for example, if we want to take 50 decimal joules and convert those to calories, then we take our 50 decimal joules times a line equals a space for answer in calories. And then what unit should go in the bottom? Joules, right? And what unit should go on top? Calories. And then what's the relationship between joules and calories? Right, 1 calorie is 4.184 joules. So you get 11.95 calories. And then when you do the significant figures on that, you get 12 calories. So that's just a straightforward unit conversion like you've been doing already in the course. Okay, let's talk about energy flow. So when we talk about thermodynamic systems, systems related to heat and changes, we tend to think of the systems that we're studying in two parts. One will be the system itself, which is the thing that we're normally studying, and then the surroundings. So that's everything outside of that system. So for example, if we are studying the melting of ice, the ice would be the system, and we would be observing that melting ice in the surroundings. So if you have a change where energy is going into the system, we call that endothermic. So endo being into the system. And if energy is coming out of the system into the surroundings, then that is exothermic, as in exit. And if you have an endothermic process, then the energy of the system is going up because energy is going into the system. So the change in energy, so delta being change, in energy is positive because the system's energy is going up. If you have an exothermic process, energy is coming out of the system, going into the surroundings, and the change in energy we consider to be negative because the system's energy is decreasing. So the system's energy is going down, so it's a negative change in energy. So when we look at these changes, we're always looking at these changes from the perspective of the system. Is the system's energy going up or is the system's energy going down? So when we think about processes, we're often thinking about processes as observers in the surrounding. So that example that I gave you of melting ice, when ice melts, we might feel cold. Like if you've got your hand on a cup of ice and your hands are on this cup of ice, we feel cold. Why do we feel cold? Energy is actually leaving us and going into the system. We're getting cold because we're losing energy. So the system is taking energy from us and using that to melt the ice. So in the surroundings, if we feel cold, if we're in the surroundings, we feel cold, that's because energy is being taken from us. Energy is going into the system, and therefore it's an endothermic process. So melting ice is actually an endothermic process. It takes energy to melt ice, and energy has to go into doing that. On the other hand, if you wanted to go the other way and take um, liquid water and turn it into ice, you've got to actually, that's an exothermic process because we've got to take energy out of the water in order to turn it into ice. Okay, so that's endothermic and exothermic. So if you're trying to decide whether something is endothermic or exothermic, if we are not the system, sometimes we might be the system because we might be thinking about energy changes happening to us. But most of the time, we're observing a system from the surroundings. And if we're getting hot, then it's usually an exothermic process. Because if we're getting hot, it's because energy is coming into the system making us hot. On the other hand, if we're getting cold, then energy is leaving us, going into the system, and it's an endothermic process. So those heat pads, the ones that you stick in your gloves and your boots, when you use those and they're getting hot, we feel hot. So would that be endothermic or exothermic? It's exothermic because we're getting hot. And so if the system is the hot pad, then it's exothermic. Okay, so that's endothermic, exothermic. So the universe is the system and the surroundings. The first law of thermodynamics is basically the idea of the law of conservation of energy, that energy is conserved. And the first law of thermodynamics is that the energy of the universe is constant. So if you're talking about a system and a surrounding and its surroundings, there is nowhere else you can get energy. So this is the idea that energy can't be created or destroyed, because if we could create energy and add energy to the universe, that would mean we would need something other than the systems and the surroundings. And the first law of thermodynamics says that there is nothing else. There is only the system and the surroundings. That's the only places you can get energy. So energy has to either come or go from the system or its surroundings. And another, so the first law of thermodynamics is basically the same idea as the law of conservation of energy. And an informal way of stating the first law of thermodynamics is that there's no free lunch. In other words, you can't get energy from nowhere. It has to come from somewhere. Energy lost by the system, if the system loses energy, that amount of energy will be gained by the surroundings. It can't just disappear. So the first law of thermodynamics and the law of conservation of energy are very similar. Okay, the kinds of changes. Um, the kinds of changes that we want to look at for this unit are changes of temperature. So the kind of thing we want to be able to do is to find out how much energy it takes to change something's temperature. So if you have a cup of water, how much energy is it going to take to change its temperature? We also want to be able to calculate the energy required for a change of state. A change of state would be changing from, say, liquid to solid, or from liquid to vapor. So that's when we That's what we're talking about when we're talking about a change of state. And we also want to be able to calculate energy for chemical changes. Chemical changes being changes from one substance to another, in other words, chemical reactions. So we want to be able to do energy changes for change of temperature, change of state, and chemical changes. Okay, so the first one we're going to do is change of temperature. So if only the temperature is changing, nothing else is changing about the system, then that's why I say no phase change. We only have one phase. So if we have a liquid, it's staying as a liquid. If it's a solid, it's staying as a solid. It's not going to be changing from solid to liquid. The equation for this is Q equals S times M times delta T. And some students have called this the Q smut equation, yes, because it looks like smut. So some students call this the Q smut equation. The Q being heat, why Q? Probably for quantity. I think H is used for other things, so that's why they're not using H. So Q for heat. S is something called the specific heat capacity. And some textbooks use C. Your textbook might use C instead. So instead of specific heat capacity, use C for capacity, just heat capacity. M for mass, and delta T is the temperature change. Again, delta for change, T for temperature. And the temperature change is the final temperature minus the initial temperature. So TF for T final minus TI for T initial. Now, if you think about this equation, it makes sense. The amount of heat required to change something's temperature depends on a few things. It depends on how much of that thing that you've got. So for example, if you have a cup of water, it's going to take a certain amount of energy to change its temperature. If you have a bathtub full of water and you're doing the same temperature change, because there's more water, it's going to take more energy. So that makes sense. That's why M is in this equation. There's dependence on mass, on how much material that you have that you're changing its temperature. The temperature change also is going to make a difference in terms of how much energy is required. So if you take a cup of water and you're changing its temperature by, say, 5 degrees, that won't take as much energy as if you're changing its temperature by 80 degrees. So if you were taking the cup of water and 2 cups of water, let's say, and you start one at 10 degrees and you increase its temperature to 15 degrees, that won't take as much energy as taking it from 10 degrees to 80 degrees. So a bigger temperature change is going to require more energy. And then there's S. So what S is about a substance's natural ability to absorb heat. And it turns out that different substances have different capacities, that's why they call it the heat capacity, have different capacities for absorbing heat. Something that has a big heat capacity takes a lot of energy to change its temperature. Something that has a small heat capacity won't take very much energy to change its temperature. So let's look at some specific heat capacities of some substances. So you'll see that some substances have very different heat capacities. So if we look at water, its specific heat capacity is 4.184 joules per every gram and degree Celsius. So for 1 gram and 1 degree Celsius, it takes 4.184 joules. And that's a number that we've seen before because that number is the same as the calorie. So basically the calorie is the heat capacity for water. 1 calorie is the amount of energy it takes to heat 1 gram of water by 1 degree Celsius. So the calorie is really the specific heat capacity. And it's 4.184 joules per gram degree Celsius. So that's water in the liquid form. For water as ice, it actually has a slightly different heat capacity. It's actually 2.03 joules per gram degree Celsius for ice. And for steam, it's pretty similar to ice, 2.0 joules per gram degree Celsius. And water actually has a fairly high heat capacity. That has to do with the hydrogen bonding in water, that it's a very sticky molecule, so to get the molecules apart, takes different amounts of energy depending on its form. If we look at a few other substances, aluminum has a heat capacity of 0.89. Iron is 0.45, and gold is 0.13. So gold has a very low heat capacity, which means that it takes very little energy to raise its temperature. So it turns out metals in general, and gold in particular, are good conductors of heat. So if you think about the kinds of applications where you want something to conduct heat or not to conduct heat, like when you're cooking, you want cooking utensils like pots and pans to be able to conduct heat well, because you want to be able to transfer the heat from your burner into whatever it is you're cooking. On the other hand, you uh, don't want to have a big change in temperature for something like an oven mitt. So if you're going to grab something that's hot, you don't want an oven mitt to change temperature very quickly. So an oven mitt should have a very high heat capacity, because you don't want it to change its temperature very quickly when you go to grab something that's hot. Okay, so let's look at an example and calculate the energy for a temperature change. So in this example, we have 100 joules of energy. It's absorbed by 25 grams of the substance, and the specific heat for that substance is 0.14 joule per gram degree Celsius. So it's got a very low heat capacity. It's a good conductor. What is the change in temperature? So as I often do, I like to summarize the word problem before solving it. So 100 joules, that's our Q. So Q is 100 joules. The mass is 25 grams. The specific heat capacity is 0.14 joule per gram degree Celsius. And the question is asking us to find the change in temperature. So in other words, delta T. So delta T equals question mark. So we need to rearrange the Q-SMUD equation for delta T. So if we do that, what needs to move, I guess? Right. So the S and the M have to move. The Q doesn't have to move. So the S and M go underneath the Q. So delta T is going to equal Q over SM. So plugging the numbers in, we have 100 joules over 0.14 joule per gram degree Celsius. And also on the bottom, we have 25 grams. And when you calculate that out, what do you get? To 8.571, and we're going to round that to actually it's 1 sig fig, because it's 100 joules. There's no decimal after the 100, so that's only 1 sig fig. So that's going to round to what? 30. One more thing we need to do. Put the unit in. So let's see what the units work out to. So our joules are going to cancel. We have joules over joules, so they cancel. Grams cancel, because you have grams over grams. So all you're left with is degrees Celsius, and degrees Celsius is in the denominator of a denominator, which means it bounces up to the numerator. So our units are degrees Celsius. So delta T is approximately equal to 30 degrees Celsius. Okay, so here's another one. And maybe I will leave this one for practice. I've got the answer here. In this one, instead of calculating change in temperature, this one is looking for the heat. So that's the Q. How much heat is required to change the temperature of 852.5 grams of iron from 40.1 degrees Celsius to 75.5 degrees Celsius. So maybe I'll leave this one for you and we'll keep moving on. So that was calculating energy for temperature change. Here's calculating energy for a phase change, a change of state. So the kind of thing that we're doing here is, say, going from between solid and liquid. And when you're going between solid and liquid, if you take a solid, turn it into a liquid, what's that called? What's the name for that process? Melting. If you go the other way, you turn something from a liquid into a solid, what's that called? Freezing. And another term for freezing is fusion. So the energy required to do that is called the molar heat of fusion. So fusion is the same as freezing. The molar heat of fusion is the energy required to melt 1 mole of solid. So it's funny that they call it the molar heat of fusion and then define it as the energy required to melt. But the energy is the same to go between melting and fusing or freezing. It's the same energy, it's just a question of whether you're putting that energy in or taking that energy out. So if you put the energy in, you can melt something. If you take the energy out, you can freeze it or fuse it. So, but it's the same amount of energy, so it's 6.02 kilojoules per mole for ice. If you're going between liquid and vapor, so if you're going from a liquid to the gas, what's that called? Vaporization, right? And if you're going from gas to liquid, condensation, right? So this is called the molar heat of vaporization. And it is the energy required to change 1 mole of liquid to vapor. For water, going from liquid water to water vapor, it's 40.6 kilojoules per mole. So the energy to go between liquid and vapor for water is quite a bit higher than between water and ice. So here's an example. If we had 40 decimal grams of ice, how much energy does it take to melt it? And water is 18.02 grams per mole. So what we need to do with this is figure out what process is going on. Then we know which molar heat to choose. So we're starting with ice and we're melting. So which of those two energies do we need? The molar heat of fusion. So the molar heat of fusion was what? Okay, 6.02 kilojoules per mole. And this being kilojoules per mole, to get the energy in kilojoules, we need to know the number of moles. So how do we convert grams to moles? Start with our grams. So it's a mole map, so GNP. So we're going from grams to moles. It's a one-step calculation. So we start with our 40 decimal grams. So we need our line, right? Equals. Actually, we're getting kilojoules because remember we're calculating energy. Oh, sorry. Yeah, sorry. We need the moles first. Yeah, I'm getting ahead of myself. We need the moles first. You're right. So what do we need on top? What do we need on bottom for units? Moles on top, grams on bottom. So the 18.02 goes in the bottom. because it's 18.02 grams per 1 mole, or 1 mole for 18.02 grams, right? .219 moles. And we would round this to 2 sig figs, but we won't right yet. So I'm going to underline it just to keep track of where we would round. And we take that number, and we use that number to get our kilojoules. So 2.219 moles times 6.02 kilojoules per mole. And that's going to give us 13.358 kilojoules. And we round that for sig figs. Becomes 13 kilojoules. Right. So we had 40 at the top. So that means we had 2 sig figs, 40 decimal grams. So that means that was 2 sig figs. So we need to round our answer to 2 sig figs. And I have the answer here at the bottom right. And so that is the correct answer. So in order to calculate a heat change, if the temperature is changing, what are you going to use? The first one, which is Q smut, right. Use Q equals SM delta T. If the state is changing, you need the molar heat of fusion or vaporization. Now, what if we've got more than one thing happening? So if we look at this, let's imagine that we are starting with a block of ice and then heating it up. So on the bottom of this graph, we have the heating time, and on the left side of it, we've got the temperature. Now let's say we're starting with a block of ice at minus 20 degrees Celsius. Can ice go to minus 20 degrees Celsius? Shouldn't ice be 0 degrees Celsius? Yeah, we can get ice below 0 degrees Celsius. Once it's in the form of ice, you can change its temperature to whatever you want it to be. Below 0. 0 is where it melts, but once you've got it in the form of solid ice, then you can keep changing its temperature and get it as low as you want it to be. So yeah, you can have ice at negative 20 degrees Celsius. So let's say that's where we're starting. So we're starting with a block of ice at minus 20 degrees Celsius. What we're going to do as we heat it, first of all, is change its temperature. So we're going to increase its temperature until it gets to the melting point, 0 degrees Celsius. At which point the temperature levels off for a bit. We keep heating it and until it's all turned into liquid water, at which point its temperature will then go up again to the boiling point. You get to the boiling point and the temperature stabilizes at 100 degrees Celsius until you've turned it all to vapor. And then once you've got it all in vapor form, then you can keep heating it up again. So again, with water vapor, we can get water vapor hotter than 100 degrees Celsius once it's in the vapor form. When it's turning to vapor, between liquid and vapor, it'll stay at the boiling point 100 degrees Celsius. So if you need to calculate this, so when you are heating from negative 20 degrees Celsius to 0 degrees Celsius, you have ice, and you are changing the temperature of the ice. So if you're calculating heat changes for temperature without a phase change, you're using Q-SMUT. Once you get to 0 degrees Celsius, you're melting. And if you need to calculate the energy change for melting, you need the molar heat of fusion. Once you've got it all melted, it's in the form of liquid. And again, to calculate the energy changes, it's Q-SMUT because you're not doing a phase change, you're just changing temperature. You get it to the boiling point, and then you're vaporizing or boiling. And here you need the molar heat of vaporization. And then, yeah, and then it's in the vapor phase, and again, it's Q-SMUT. You're right. And just one little note about vapor. Vapor and steam are slightly different. Steam is sort of when you can see water condensed in, that's what a cloud is. So it's water condensed in the air. So strictly speaking, that's steam. So steam and water vapor are not exactly the same. Often I'll use them in the same sense, but strictly speaking, water vapor is slightly different from steam. Okay, so now if you want to do a calculation of the energy changes for doing a number of these things, you have to do them all separately and then add them up. So for example, let's say we wanted to take river water, 1,000 kilograms of it, and its temperature is 10 degrees Celsius, and then we want to turn it into vapor at 600 degrees Celsius to run the steam turbine of a power plant. Well, to do that, we're going to have to calculate each step separately. So if we go back to the diagram here, we have liquid water at 10 degrees Celsius. So we're going to have to increase its temperature to get it to the boiling point. Then we're going to have to turn into vapor, and then we're going to have to heat it up again to 600 degrees Celsius. So there's actually 3 steps to this calculation. So I have put these 3 steps down. We've got to change the water to 100 degrees Celsius, which is a Q-SMUT equation. We have to vaporize it. So that's a molar heat of vaporization type question. Then we've got to get it from 100 degrees Celsius to 600 degrees Celsius, and that's a Q-SMUT. And then we have to add all 3 of those together. So this one's actually quite a long problem. So we have the S. We need the S for liquid water. You remember what that is? Nope, not 6.02. 4.184 joule per gram degree Celsius. That's the specific heat capacity for water. Times, we need the mass of water. We have 1,000 kilograms. The heat capacity is in grams, though, so we need to convert 1,000 kilograms to grams. So 1,000 kilograms, we do this over here, 1,000 kilograms times, and do you remember the relationship between kilograms and grams? 1,000 grams in a kilogram. So that would be 10 to the 6, or 1 million grams. So we have 10 to the 6 grams times the change in temperature. And we're going from 10 degrees to 100 degrees. So what's our delta T? 90 degrees. So 100 minus 10 gives us 90 degrees. And our grams will cancel. Our degrees Celsius will cancel. That will leave us with an answer in joules. It is a big number. 3765, 6, and then 5 zeros. So if we do it in scientific notation, 1, 2, 4, 5, 6, 7, 8, 9 times 10 to the 9 joules. Okay, so that's changing the water just to 100 degrees Celsius. Now we've got to vaporize it. And the molar heat of vaporization is 40.6 kilojoules per mole. And we have 10 to the 6 grams, so we need to convert that to moles. So 10 to the 6 grams, and over here on the left, I have the calculation of the molar mass of water. 2 hydrogens and 1 oxygen adds up to 18.02 grams per mole. So we have to have moles on the bottom, grams on top, because our target is, nope, that's the other way around. We're looking for moles. Grams on the bottom, moles on top, and 1 mole is 18.02 grams, which works out to 55.4938.96 moles. Okay, now we take that, we multiply it by 40.6 kilojoules per mole. It's probably more sig figs than we need, but we'll go with that for the moment. Two, 2, 5, 3, 0, 5, 2, 1. I won't do the decimals. I'll just go with that. And that's in kilojoules. Okay. Let's put a little box around that. And we had that. Okay, so our third step is then, again, to change the temperature. So we need the heat capacity for water vapor, which I remember correctly was 2.0 joules per gram degree Celsius. We have 10 to the 6 grams of water. And this time we're going from 100 degrees to 600 degrees. So what's our delta T? 500 degrees Celsius. So 600 minus 100 gives us 500. And it's 500 decimal degrees Celsius. And when you calculate that out, what do you get? times 10 to the 10 joules. All right, so now we have all our energies. We need to add them up. Adding them up may not be, isn't really so straightforward, and I'll show you why in a moment. Let's put all our numbers together. So we have 3.7656 times 10 to the 9 joules. Oops. And we had 225.3052. And then we had 1 times 10 to the 10th joules. So you've got to get them all to the same unit before you can add them up. So you can either convert them both to joules or convert them all to kilojoules. It's probably better to go to kilojoules. We could go to, you can go either way. Just because we're dealing with such big numbers, going to kilojoules is going to reduce the numbers a little bit. So to go from joules to kilojoules, you need to divide by 1,000. So this will become 3.7656 times 10 to the 6th joules. Kilojoules, sorry. We were converting to kilojoules. And 1 times 10 to the 10 will become 1 times 10 to the 7th kilojoules. And this one was 2.253051 times 10 to the 1, 2, 6, 7, 10 to the 7, 7 kilojoules. So now we could add all these up, but again, there's another issue with adding these up. In order to keep track of the sig figs, it's easier if they're all in the same power of 10. So we've got 2 of them as 10 to the 7th, so we could convert this first number from 10 to the 6th to 10 to the 7th, so make it 0.37 times 10 to the 7th. And when you add all those up, what do you get? Three, 6, 2, 9, 6, 1, 2, 1 kilojoules. And then now we need to go figure out how many sig figs. So we go back all the way up here to the top. Our grams had only 1 sig fig in it because it was 1,000 kilograms, and that's only got 1 sig fig. So consequently, we only have 1 sig fig which was significant, and I think that is true of all of our calculations. It was just 1 sig fig that was significant. So consequently, really it's only the 3 which would be significant. So we need to round that. Becomes a 4 times 10 to the 7th kilojoules. And I have an answer down below as 4 times 10 to the 6 kilojoules, so we may have lost a power of 10 in there somewhere, or we actually didn't lose. We gained a power of 10 somewhere. So we need to go back and look and see if we can find where the mistake is. So that might be a little tricky. So for those of you watching on video, I'm just going to pause for a moment while we track down our error. Okay, look, we just did some troubleshooting and found a calculator error. So on the calculator, we had we're using the exponent function on the calculator, and 10 to the 6 was being entered as 10 EE6 instead of 1 EE6. And 10 to the 6 in a calculator should be entered as 1 EE6, in other words, 1 times 10 to the 6 instead of 10 times 10 to the 6. So that means that all our numbers are 10 times too high. So that means our 10 to the 9 here should really be a 10 to the 8th. And for this number here, our decimal is in the wrong place. So this number is 10 times too high. So the decimal should have been here. And the decimal should be here. So then this number also should be a 10 to the 9. And then, so this number should be 10 to the 8th. And then this number is 10 to the 6th. And then this number should be a 10 to the 6th. And this number should be 10 to the 6th. And this number here was 10 to the 9th. And this one should have a decimal here. So that means our answer actually is 10 to the 6th. So there we go. That agrees with the answer that I had there already. So for those of you on video, apologies for that. That's one of those things that can happen. Sometimes we have to track down an error in calculation. Okay, so that was thermodynamics. That was calculating energy changes related to temperature changes and phase changes. Now we're doing thermochemistry, which is the chemistry of heat changes. We're doing heat changes for chemical changes, for chemical reactions. What happens with energy in a chemical reaction is you start off with your reactants, which are going to have a certain energy. And at the end of the reaction, you will have your products, which will have a different energy. The energy that you get out of the reaction is the difference between the energy of the reactants and the products. So that's the energy released to the surroundings in this case, because we have an exothermic process, because the energy of our products is less than the energy of our reactants, so we're getting some energy back. But in between your reactants and products, there's often an energy hump. The energy hump is called the activation energy. So often chemical reactions won't get started until they get a certain amount of energy. So that's why wood, for example, doesn't spontaneously burst into flame. So in this classroom, we have lots of things made out of wood, and they don't just suddenly burst into flame. The reason is that they will burn, but they need some energy to get that reaction going. Once you get the reaction going, you'll get enough energy back that it can keep the reaction going, but you need a significant amount of energy to get that reaction started, and that's what the activation energy is. And the reason for that, if you think about what's happening on a molecular level, the model we have in mind for chemical reactions is that molecules have to run into each other. They have to get into close enough proximity that the atoms can rearrange themselves. But not only that, they have to run into each other with enough energy. They have to collide with enough energy that you can break some of the existing bonds in the molecules before you can start forming new ones. So it's going to take some energy to break the existing bonds in a molecule to pull the atoms apart before they can start rearranging themselves. So that's what the activation energy is going to do. So once you get that energy back, the potential energy that was stored in the chemical bonds, so if it's an exothermic reaction where you get the energy back, then you can make use of that energy in the form of heat or light. So for example, the gasoline in your car. When you burn that, you get some energy back, and then you can use that energy to do work, like move your car from one place to another. So there is a term used in thermochemistry called enthalpy. Enthalpy is a measure of energy. It's often used to represent the energy changes of chemical reactions. Something I haven't talked about is that it's a state function. A state function is a function that only depends on the initial and the final states, as opposed to a path function which depends on the pathway by which you got there. So the distance from your home to campus here would be a state function. The distance, the direct line distance, only depends on where the two places are. How much energy used to get here is a path function. So for example, let's say you left home, you drove to campus, then you suddenly realized you forgot your books. So then you drove home again. You got your books. And you're driving to campus, then you realize, oh, you need some groceries. So you stop at the grocery store. And then after you stop at the grocery store, you're really stressed out. So then you stop at the liquor store, and then, you go back home to drop off your groceries and your beer at home, and then finally you make your way back to campus. So, that was a long route to get to campus, and you burned a lot of gas to do that. So that's a path function. So the amount of gas that you burn to do that would be a path function. But the straight line distance between your home and campus, that's just a state function. So for exothermic processes, enthalpy is negative, which is the same. The system's losing energy, so it's negative. And the symbol used for enthalpy is H. H for heat. Hess's law says that, basically it says that enthalpy is a state function, that all you really need to know about are the initial and the final states. So if you're calculating the energy change for a chemical reaction, you don't really need to know the whole pathway. You don't need to know exactly how it does it. All you need to know are the energies of the initial and the final states, and then you can calculate the energy change. So that's what Hess's law is really about, that enthalpy is a state function. So the application for Hess's law is that if we want to know the energy change, the enthalpy change for a particular reaction, we don't have to know the exact pathway by which this reaction takes place. If we can find any pathway and we can find the energy of any pathway, then we can calculate the energy change. And there are standard tables of energy changes. So people have measured the energy changes for certain reactions, and they put that information into tables, which you can look up in the textbooks or reference books, or maybe now on the internet. And if you find a set of reactions that when you add up these reactions, they get the reaction you're interested in, then that means you can just add up the energies and you'll get the energy of the reaction you're interested in. So for example, so this is at the top here, N2 plus 2O2 yields 2NO2. That is the energy change we're interested in. If we add up these two reactions, maybe we can get the energy change that we're interested in. So if we add up the left side and the right sides of this equation, so we have N2 plus, and we have two oxygens, so 2O2 plus 2NO. So that's adding everything on the left side. And on the right side, we have 2NO and 2NO2. Now let's look on the left and the right side and see if there's anything that is the same. Looks like our two NOs are the same. And just like in a math equation, if you have two things which are the same on both sides of an equal sign, then you can get rid of them. And that leaves us with N2 plus 2O2 yields 2NO2, which turns out to be the equation that we were interested in. So this may not be the exact pathway by which that equation or that, the chemical process happens, but that's okay. It doesn't matter. Any pathway will work because um, enthalpy is a state function. So now if we just add up our delta H's, so 180 kilojoules minus 112 kilojoules, and what do you get when you do that? 60? 68 kilojoules. So if we look at the first equation, the N2 plus O2 yields 2NO, it was 180 kilojoules, and it's positive. And if it's positive, that means that step is endothermic. The next step is negative 112, and because it's negative, it's exothermic. Remember, positive means energy, the system's energy is going up, so it's endothermic. Negative, the system's energy is going down, so it's exothermic. So the process that we were interested in, is it exothermic or endothermic? It is endothermic, right? Because it's positive. So if you have an equation that you're interested in finding out the energy of, then what you would do is to look in a table of standard equations, and then you need to find some combination that when you add up those equations, they give you the equation you're interested in. In order to do that, there are some things that you might need to do. You might need to modify those equations a little bit. You might need to reverse an equation, and if you reverse an equation, you change the sign of the delta H. Because if we look at one of these equations here, if you run the equation forward, so this N2 plus O2 yields 2 NO equations, running it forward, it's endothermic, so it takes this much energy to go from reactants to products. If you run the reaction the other way, that amount of energy you'll get back. So that amount of energy will come out. So when you just reverse an equation, the sign on the delta H changes. Sometimes you might need to multiply an equation by a factor. In other words, you might need to do that equation more than once. So you might need to do that equation twice or three times in order to get enough of the molecules that you need, that when you add up the equations, you get the equation you're interested in. So basically, if you do this equation once, you get this much energy out. If you were to do this equation again, in other words, you're doubling it, multiplying everything by 2, you're going to double that because you do the reaction twice, you get twice as much energy out. So those are the two things that you might need to do in terms of adding up these equations. So, for example, here's another example of a Hess's law type problem. Let's say we're going from graphite to diamond. So the two forms of carbon, we want to know the delta H for it. The process we may not know exactly, but if you look in a table of standard equations, you can find equations for the oxidation, basically when you burn graphite and when you burn diamond, turning them into carbon dioxide. And they have determined the delta H's for these. So what we need to do is to be able to find some combination of these two equations that when we add them up we'll get the equation we're interested in, which is the one above. So we want to get this equation. So can you think of how we might add up these two equations to get the equation we're interested in? So if you look at this, we're starting with graphite. So we need to run this equation that way because this equation has got graphite at the start. See, this equation ends with diamond, but this second equation starts with diamond. So that means we're going to have to reverse that equation. So the first equation we can keep running as it is. Second equation we're going to have to reverse. So let's rewrite these equations. So C graphite plus O2 yields CO2. And then second equation we're going to reverse. So in other words, CO2 goes to C diamond plus O2. And when you do these, very often there is an intermediate. And in this case, CO2 is the intermediate because basically one equation is producing CO2, the other equation is consuming CO2. So the CO2 is going to disappear when you add these two up. So that's called an intermediate product because it won't show up in the final equation. It's an intermediate thing that gets used up. So when we add these two up, we get C graphite plus O2 plus CO2. And then on the right side, we have C diamond. Oh, wait, sorry, let's do it top to bottom. So we have CO2 plus C diamond plus O2. And if we look for things on the right and the left side, we have O2. So it looks like O2 is also an intermediate. And then we have CO2 on both sides. So adding up these two equations does give us the equation we're interested in because we want C graphite going to C diamond. So adding up the equations in this form does give us what we want. Now we need the delta H's for these two things. So the delta H for the first one is the same as it was because we didn't change it, negative 394 kilojoules. The delta H for the second, we need to change its sign because we reversed the equation. So it's going to become positive 396 kilojoules. So we add up negative 394 and 396 kilojoules. And we end up with 2 kilojoules. So the delta H going from graphite to diamond is 2 kilojoules. So is this endothermic or exothermic? Endo. So if we want to turn graphite into diamonds, we're going to have to put some energy in to do that. Okay, so I've got some practice problems for you to do, and so I've got a sheet of practice problems which you can either print off from the S drive or I will give you, and you can do those, and the answers for those are here. So we have S plus O2 going to SO2, and then down below we have 2O3 going to 3O2, so that's ozone to oxygen. No, that's a different one than I have on the practice sheet that I've given to the class here. No, that's right. So, okay, so these are the equations I've given on the practice sheet. And on the practice sheet, I've also given some standard equations as well. So what you need to do is to figure out how to add up the standard equations that I've given to give the equation that's of interest, and then add up the delta h's. So either change the sign or multiply by a factor if you need to calculate the correct delta h. So that's it for the lesson, and the answers are here, so you can use those to check your work for the practice problems. And if you have any questions, then let me know. And that's it for the thermochemistry lesson.